So this class we are going to discuss about the recursions, and the recursions is as I said before, it is an advanced programming technique. In fact, it is used for all possible programming languages. What does it mean? The at a very high level, a recursive function is a function that call itself. You know, you have a function you have a function. I mean, you know the C++ function, that's very standard. But a recursive function is a special function that calls itself. So that is the very basic concept of recursive function. And that's where we find the reference of recursion. So let's say, I mean, we write a simple function, let's say void message. I'm just abbreviating this one a little bit. So at a very basic level, you have this function, right? And recursive function will be simply like message, so it will call itself. It's a fun stuff, but we are going to explore more on the recursion. So let's move on. So it's pretty much, you can see here, you have a recursive function like countdown, let us say that is a recursive function. So this is a function that does not return anything, not a value returning function. Now you have one argument called number, num, the number. So what it says, if the number equals 0, then blast off means you are done. I mean, you start something. Otherwise, you can print the number and then you can just call countdown. So you have countdown number minus 1. So this is called the recursive call. So what happens here? You know, if, this is, there are two things that you need to consider whenever you design a recursive function. Number one is you have to find out the default case, the exit case, default or exit case, exit situation. There must be some exit pathway from the function, otherwise it will run infinitely. And then number two is the recursive logic. I mean, actual recursion. So function calling itself, that part. So it does not mean that you, I mean, just in the last slide I wrote this one, this will be a runoff because it will keep calling itself. So there should be some weight, some logic to exit, to escape these recursive calls. Okay, so this is our part. So here the logic to exit the function is this one. Because suppose you put num equals 4. So what happens in the first step? You enter the function num not equals 0. So we go to the else block and then we print the num. So we print 4 and then we call countdown again with number minus 1 as an argument. So we get 3 here. This is again not equal 0. So here we print 3. I mean, of course, you have to get these triple dots. Then we call countdown again. So it becomes num2, right? 3 minus 1 equals 2. So here comes 2. So when it comes to be 2, then we have again num not equals 0. It's not 0, so it will go to else. So we will print 2 here. And then comes 2 minus 1, 1. So we are calling countdown 1. So here, so once you go to 1, again it's not equal 0, so it goes here. So we get 1 printed. And then finally we get num 0. So it meets its exit condition, escape condition. So then so it becomes 0 next argument. So num equals 0, then you write blast off. So that will be the execution. So that is our recursive function. I mean, at the heart of it, it is simply like that. Okay. So I mean, all the recursive functions may not be as simple as this one, but there are two components, as I said, that is your escape situation, because otherwise you will recurse infinitely. So it will be equivalent to an infinite loop. So we don't want that. So in order to in order to escape from the infinite loop, we have to have some exit criteria. So a recursive call should have one like recursive property, that is the core property, and also one escape property. There are two components of any recursive function. So recursion, whenever we do the recursion, we typically implement it in a function. It's a recursive function call, and a recursive function contains two components. One is the exit path or escape path. Another is the recursive property. These two. So that's what we just described. So we don't need to go through here. So we called it. So when you next part is solving problems with recursion. So recursive functions, why we use the recursive function? They are, I mean, these recursive functions are used to improve the performance of complex problems, you know. Basically what you do, improve the performance and to make it simpler. So what we do, we break the problem into multiple situations, you know. In the mathematics, if you have done any maths, I mean in the past or even right now, if you are taking some maths, you will find that there is a process in mathematics called the method of induction. What does it mean? It basically tries your expression with some known values. I mean, it may not be exactly like recursion, but I'm just drawing some parallel example. So, when you have an inductive method or induction, it means you try the function with some simple values. Let's say you have a function fx, and let's say you have a very complex function fx, and then it is equal to x to the power 5 plus a x to the power 4 plus c b log x. So it's a very complex function, and then let's say c e to the power x square. So it's a very arbitrary, very complex function. You cannot work it out by piece of paper. So an induction method, what it does, basically it inputs some values of x. So it inputs some value, let's say 1. What happens if it is 1? What happens if it is 2? And in that way, it finds some pattern, and then it implements that pattern to solve the problem. Now, in the recursion, we do a similar kind of, we encounter a similar kind of situation. So let's say we are doing a countdown, right? I mean, in the countdown problem that we described before, if you wanted to do the countdown with you could do it with a for loop as well, without any issue. But when you do the for loop, then basically what you are doing there, you have to control, you have to give everything in the beginning of the process itself. Like you have to set the limits and you have to predict how you can exit. I mean, it's a very complex, I mean, not complex, I mean, it's a lot of planning, pre-planning. So the, the every problem that you use to solve your with a program may not be like the countdown. It can be much more complex than countdown. Maybe you are doing some binary search, you know, That's not very straightforward problem. So in those cases, what you do, you simply define in the very beginning that at this point, if I find let's say we are doing some binary search. Forget about binary, just think about search. If you do a search, then if you find the value, you have a value in the argument. Whenever your value equals the value of the I mean whatever evaluated, let's say you are finding a value in an array. So your array function, whenever you find the value, that is your exit point. But then, other than that, you are doing the recursive calls. So that recursive calls we are going to learn, and also we will plug in some exit logic. So recursive function is used to simplify a problem. It breaks up the problem in its very simple format so that we understand just by regular notion what is going on. And the simple solved problem is known as the base case. The base case is the exit path. I mean, whenever you find the base case, then you just say that you solved the problem. So base case is just like exit path. Whenever you search something, you find the solution, you find the exact number, they match. That means your base case is found, you know, and it's just like that. I mean, the different problems can be solved in a different way. You cannot find that a universal way to solve all problem. Let us say if you want to sort something, or if you want to, yeah, let's say if you want to sort something, it always means that you are comparing objects, or maybe you may find a problem that requires you to find the minimum, let's say minimum value. So it's basically you have to compare, you have to think about an array, and then you keep comparing the values with each of them. Now, if you try to do it in a using a for loop or while loop, it will be a multiple. I mean, it will take a very complex situation, because you have to compare each value with each other value, and then you calculate the max or mean, and then you go to the next value, and so on. So it will be a super complex problem. Let's say you have 1 million numbers to compare. But then if you use the recursion, we will see that it becomes very pretty simple. I mean, we divide the whole array into, I mean, whole set of numbers into small pieces, and then we will find for each piece we will find a recursive call, and then finally once we find the base case, that is no other value that is less than that particular value, then that's the minimum. That will be the base case, and that's how we will organize our problem. I mean, solution, not the problem. So a recursive function should always, so this is, I have been saying this always, that you should have always a base case, or your exit pathway or escape route from the recursive function. In a sample, in the program that we discussed, this is the base case. The number equals 0. So there is no more countdown. The event is happening right now. So that's pretty much the recursive call. Let's show some example. Let's take some opportunity to find some example of recursive call. Just a second. Something else fired up on my computer. Okay, that's okay. So let's have our VS Code ready. Let's open the folder, possibly the classwork 5, today's one, and let me close this one, and then let me open a file. So we can say uh, recursion example 1.cpp. So let's start with this one. It's a simple, let's write a simple program involving the recursion. So as usual, we can start with that famous headers like this, and then we can create a function prototype. Let's say we are defining some simple stuff. What can it be? So let's say we are trying to solve the problem of we are trying to find the factorial of five numbers. I think you all know about the factorial, right? So just to give an overview, quick overview, you know, maybe you know it already, but let's revisit this one. Let's say you have factorial 5. So what does it mean? You express factorial with this exclamatory sign. Factorial 5 means basically 1 times 2 times 3 times 4 times 5. So whatever is the number, you just multiply each number from the beginning of the count, like from 1 to 5. You keep on taking getting the product of each number. So that's your factorial 5. So we can solve this is an ideal candidate for your recursive call. So how can we do that? Let's say we define first thing first a function that will calculate our factorial. So we call it factorial, and it's an integer. And of course, I mean, you cannot find the factorial for the real numbers, I mean the double numbers or floating point numbers. That does not make any sense simply. So now we can do main function, okay, and we can do the shell return 0. So let's get a number. Let's call the user to provide us with a number. We can tell them just send us a number. So basically we can write this as follows. So you can say the integer, enter an integer value, and it will display its factorial. So number, so it has to be, we have to define the number, int number. So this is our number that user will input to your program. So once you do that, then you can, I mean, the program's basic logic would be that you have to write cout. You can say the factorial of the number, of course. Sorry, not this one. Number is, so you are building your ground. Then you have to call factorial, the function cout factorial. That's it. And then number, but we have to yet code the factorial function. This is a prototype, so it will not give you any result. So we have to write it, and we can write it below. So what you can do here, it's very simple. Let's start by writing it. Factorial, say we have integer n. Okay. So once we get int n, then once we get int n, we can do just like if n equals 0, then you do return 1, because that's the base case for a factorial. You have like if n equals 0, factorial of 0 is not nothing but 1. That is the first principle, you know. That's how things are defined. It's not like it's not a 0 means nothing, right? I mean, so you start with 1. That is the way the mathematical function is defined. Else you can say you can now you can do return n times factorial n minus 1. So there is a very nice trick that happened here. So what we did, we actually handed over the problem to the system itself. Because you see here, your factorial formula, if you think about the factorial formula, this one, 5. So 5 factorial can be solved like you write the 5 first, then 5 times 5 minus 1, then you do 5 minus 2, and you go on. I mean, 5 minus 3 times 5 minus 4 minus 4. Okay, and then of course that becomes 5 factorial actually. So in the programming solution, what we did the similar thing, but here what we did is that so we started with a number. So we started with a number that you entered, the user enters. Let's say it's 5. Then what happens? You start with 5. N is 5. 5 times 4. That is your first step. Then what happens here? Factorial minus 1, 5 times factorial 4. Now factorial 4 is, so you have the previous thing, I mean, like you have n means 5 times factorial 4, then it comes here, then you do 4 times factorial whatever, I mean, so your factorial, I mean, factorial 5 is evaluated to be 5 times x. X is factorial n minus 1. Then that becomes, I mean, that rotates like until you get 0. At that point here you hit this base case, and you will find uh, at that point it will return 1. So once you hit the base case, your factorial will be evaluated to be 1 because it will not come here. It will be 1, and as a result, at the last step, you will have like 5, then 4, then 3, then 2, then 1, and then it will be multiplied by 1. So finally, you will get the factorial 5 to be uh, 1 times 2 times 3 times 2 times 4 times 5. So in order to see the regular, I mean constant succession of the values, let's see what becomes the value. I mean, let's calculate. Let's see the values here. So let's do it. I mean, C out n. So we know which value is coming here. Now let's try to do the compilation. Let's compile the program. So the name of the program is recursion. Yeah. So dot slash fact dot exe. So now let's put the number 5. Let's put the 5. So you can see that once we are in the 5, first number we print is 5. So your factorial's value in the first step should be 5. Then 5 times factorial n minus 1. You don't know, that's x. Then it becomes 5 times 4, because always you are getting the product. Then it becomes 5 times 3, 5 times 2, 5 times 1. So finally the ultimate number is 120. So that's how you calculate your factorial. So you could give a larger number as well, like for example factorial of 100. So you will get, but it is blowing up because it's factorial of 100 is 100. That's not good. What's going on here? Let's get it off. I think it blew up. The calculation blew up because of the uh, too many digits. Let's say factorial of 7. So if you have factorial of 7, it's not good. It's not right. Something is not right. Factorial of 7 cannot be factorial of cannot be 7. So 6 times, what happened to it? Something has happened to the program. So if I do that, factor this, let's say 3. So 6, that is, this is correct. So 6, that's 2. 6 is 720. Then we do 7. Yeah, now it's good. Something happened. I mean, with the compilation, something had happened. Probably I missed something somewhere. That's why it happened. So then let's say factorial of 10. I mean, you can keep on calculating. Factorial of 100, I don't think you will be able to calculate ever, because it's a zero, because it's blow up. It will blow up because so many digits it cannot support. Let's say factorial of uh, 20. Can it support? Yeah, it's an unreal number because it blows up. It's different. So we can say factorial of 12, let's say. You can calculate this. So long as it's a smaller number, you should be able to keep calculating the factorials. So that's the way we calculated the factorial, and it's an illustration of our recursive programming, recursive function. Let's move on. So yeah, we did that. Now, so stopping the recursion is most important part. So in case of factorial, how did we stop? We just say that here, this is the factorial function. If n equals 0, we return 1. That's how we stopped. This is our base case or stopping point or exit point or escape point, whatever way you define. So each time when you call a recursive function, a new copy of the function runs. So it's the behind the scene, the memory, the way the memory manages this recursive call is as follows. Like you do, you call a recursive function every time you run it, it basically runs a new copy of the function. So when you have a single non-recursive function, your memory loads a copy of the function and runs it. So whenever you have have a recursive call, then each time you are calling the function, then it creates its own copy in the memory and it renders the value. So that's how it is done. Now each copy, as they completes their execution, they return to the copy of the function that called it, that returns. So that's what happened with the factorial. When the initial copy finishes executing, it returns to the part of the program that made the initial call to the function. So basically it keeps on referring the initial point, I mean just the previous point where the program called it. So it integrates the the results along with that. That's why when we calculated factorial 5, we started with 5, then 5 times another factorial. So it keeps on going. So if you could if you could do it like if you could illustrate it physically, it would look like in on your screen 5 and then again factorial 5. So 4 comes, then comes another factorial 3 comes, then factorial 2 comes. So then 2 times factorial 2, then 2 times factorial, then 1 time factorial 1, and then final 1 because it becomes 0. So n equals 0 means factorial 1. So that should be your result here. That's what happened with the function. So that's how it calculates. I mean, don't think it like as a vertical aspect, like something completed, next comes something. It's not like that. Whenever you calculate the factorial function, your horizontally this gets evaluated. Like what I say by horizontally is that here it keeps on, I mean, keeps on multiplication. This multiplication keeps on growing, multiplication thing. So factorial, if more the value of n, more number of horizontal rows here. And finally, you get the ultimate result whenever you hit the base case. So that's illustration. That's what we were talking. It's not a vertical. I mean, it's not a for loop. If you had a for loop, then one thing is completed, then comes the next step. So you have to manually just keep track of the things like in the program. But in factor, whenever you do it with recursive part, you are basically handing the payload to the system and let the system do the things for you. So that way, your programming effort will be much less, and in fact, the memory will like it. Your C++ memory will like it, and they will that will be much less costly, and we can even mathematically prove that, but I'm not going to do that route at this point. Now there can be different types of recursion. There is a direct recursion, that's what we call right now. A function calls itself, that's what we have done so far. But there can be indirect recursion, like function A calls the function B, and function B calls function A, and then function A calls function B, which calls, and so on, and then which calls A. So it may not be like very straightforward like what we have done. But in computer science, in the programming landscape, maximum problem that we solve, it's kind of direct recursion because it's easier to code. But indirect recursion, if you code it, you have to do a lot of testing before you actually turn it into a production mode, because there are more rooms to make some miscalculation. Because that's the good and bad thing about the recursion. The good thing is, I mean, you verify it for certain values and it works perfectly, but then you expand the range, then it starts failing, because there can be many edge cases, especially whenever you use it indirectly. So that's why when you do the recursion, it is always recommended for you to test it thoroughly. So we have done it, so no need for doing this one anymore. So there is another problem, recursive GCD function. Okay, so this is another stuff that you might want to do. So greatest common divisor is the largest factor that two integers have in common. You know, so let's say, I mean, there can be GCD calculators online. You can find it, GCD online. So I'm just bringing one up so that we know exactly what we are talking about. So let's say we have this one, and uh, we have number one. Let's say what's happening here. Yeah, that's fine. So number one, maybe you can find 20, and number two is, let's say, 40. Okay, so GCD is 20. So that is the greatest common factor that is divisible by, I mean, these two factors is divisible by maximum this number. For example, if you use 40, 20 is not really divisible. It's a whole number concept, it's not fractional concept. So if you think about let's say 5 and let's say 35, so the greatest common divisor is 5, because there cannot be anything less than that. So let's say you have the 25 and 35. So that's a really good problem to solve. So there you find the 5, because if you use any other number, you cannot divide both of them. Like 25 is divided by 25. That's the greatest number, but 25 is not divisible by 35. So that is the answer is 5. So that's how you calculate GCD. But here, what you can do here is that you can compute it using Euclid's algorithm. So basically, it says that GCD xy, I mean GCD of x and y is y, if y divides x evenly. So that's what we saw, like 10 and 20, GCD 10, x is equal to 10, y equals 20. So it will be, sorry, x equal 20, y is equal to 10. Then it will be 10 because y divides x evenly. Because 20 by 10 is 2. That is an even division. But then GCD x y equals GCD y x remainder of, modulus of y, that will be the value. So that is your clue to the recursive function. Otherwise, you can say GCD xy equals y is the base case. So basically, you have two cases here. Number one is GCD xy equals y. That is your base case. And number two is the recursive case. You have to keep on doing recursion until you find this base case. So you have to keep on doing these recursive steps until you find, I'm writing number two as the base case, until you find this base case. Okay. So how does the program look like? So it's very simple. You can see here, you can say if x remainder y equals 0. So basically what it says is that if y is divided by x, if x is divided by y and there is no remainder at all, you know what I'm understanding, right? X divided by y, for example, if you have 20 and 10, so 20 modulus of 10, that means what is the remainder? 20 by 10 equals 2, and then remainder is 0, right? So your remainder is 0. So that's what it is happening here. So if it is like that, then it is 10, this one. And in fact, that is the GCD. Otherwise, you have to return GCD y, and then you keep finding x modulo y. So let's say we are talking about uh, remainder of, let's say GCD of let's say 5 and 3. Okay, where x equals 5, y equals 3. Then what you do in the first step, this is not correct, right? We come here, then it becomes 5, and your x by y means 5 remainder of modulo of y, so it is 2. So then we are calculating GCD of 5 and 2. Then we go to here, and then it's not yet base case. So what we do next? We do um, 5, it becomes 5, y is 5, but x equals um, basically x remainder y. That means you have to calculate. Sorry, it's wrong. I'm not doing it right. Sorry. You start with 5. I mean, yeah, 5, and this is 3. So you come here. This becomes 3, first step, and this becomes uh, 5 by 3. 5 remainder 3. That means 2. 3 and 2. So in the second step, you come here. Uh, so what happens here? Your y is 3, so you are still using 3, right? You have 5 3, yeah, that's right. I mean, you have x, so okay, so your GCD becomes x, y equals, now this one, x becomes y, so you have to calculate, like you have y equals 3, now you put 3 2, then you are calculating GCD y x by y, x remainder y, so your x becomes 3 right now, and this becomes 1. So ultimately here comes the point. Here 3 divided by 1, here 3 divided by 1, I mean modulo 1, not divided by. There is no reminder, so it should be 0. So we hit the base case, and so we find it to be 1. The GCD of 5 and 3 is found to be 1. That's how it is calculated. So if we compare with the calculated value, it should look like this one. So let's say first function, we have some problem with this website. Okay, so if we do um, x equals 5, y equals 3, and we solve, this is 1. So that's actually the recursive call also gives us the same result. So that's another example of our recursive function. Let's see if we can incorporate it any in any way. So let's find out the GCD. So let's create another file, gcd.cpp. What is happening? Okay. So here, what we can do, we can start with that input-output stream. That's simple stuff. And then what we can do, we can just create the function prototype. It's a very regular kind of, we can make it a pattern. Then we can call the main function int main, and then we can return 0. Okay. So now what we can do, we can start doing int n1 and n2. These are the two functions for which the GCD needs to be determined. So let's say we get the two numbers from the user. We can say cout, and then we can say um, enter two numbers. Of course, integer numbers. When I say numbers here, I mean integer only. So that's it. And then we can do cin n1 and n2. That's pretty simple, easy case. And then we can calculate the GCD. So we can say cout GCD n1 n2 equals. So we will do the calculation now. So we can say GCD um, n1 um, n2. Okay. So if we do that, sorry, n1, not m1, it should be n1. Now we can implement the function. So we can say integer GCD integer n1 integer. Let's not put n, let's put x integer y so that we can generalize this stuff. Then we can say if x remainder y, that's what we coded, right? Y equals 0. That means there is no, it's perfectly divided. Y can be perfectly, x can be perfectly divided by y without any remainder. Then you can say return y, whichever number it is divided by. I mean, this one needs to be returned. Else, your recursive situation. So this is your base case, right? This one is your base case. And now we can find our recursive case, and that which is something like, we can say return, then GCD, you can write y, and then just the first, this one, you can just copy and paste it here. So yeah, Now you are making it the problem of C++, not your problem. Now they will calculate it for you. So you can say G++ compiling the program dash recursive.exe, and then we can say GCD, this one, some problems. Oh, sorry, G++ dash O. So dot rec.exe if we do. So you can enter two numbers, let's say 110 and let's say 45. So you will get the GCD of that is 5. I mean, it's what happened to it? There was some problem, looks like. Yeah, it's 5 because it took little time. That's why. So let's say just a second. So I think the problem is when we do that GCD, I mean, this calculation took little time. So what we can do here, we can say int result equals GCD n1 n2. Then we can print the final result, because that way it will not be waiting on anything. So end line, that will be better. I think this solution will be better for viewing the stuff. So we can recompile it, or sorry, not, we did not recompile. So we recompile it and then we run it, and you will find, let's say, same number we can put 110 and 45, and you will see, I mean, calculation is, it's not good. So what happened to it? It did not calculate something. So GCD, you are doing this one. So I think we are doing it correct, right? GCD n1 n2 equals this one. It waits for a long time and then it stops somehow. So let's say 5 and 2, if I do, it keeps on doing stuff and then it suddenly stops. Oh, I think I got it, why it is happening. It should not be comma separated. That's the problem. You can do 5 and 2 maybe. Yeah, that's how. That's why, because it's confusing the system. So we can do 110 and 45, two numbers. So you got it 5. You can find out other numbers as well, 1987 and 3, let's say. So you get it 1. Let's say another example, 1, I mean 2004, let us say. So your GCD is 4. So that's all that's all about our problem for the GCD. So we are in the halfway to the recursion kind of. So let's give a break, quick break, 10 minutes, and we'll be back and complete the rest of the parts. And I have seen some emails, one of the emails regarding some issue with the pop quiz. I will take a look at it after this class. So let's move on. So we are solving recursively defined problems now. Now, what are the problems? We call them recursively defined problems. The natural definition of some problems may lead to a recursive solution. For example, Fibonacci numbers, that's one of the examples that can be a recursive. It's recursive in by nature. So you see here, after starting 0, 1, each number is the sum of two preceding numbers. So basically, this one plus this one should be the third number, and then 1 plus 2 should be 3, then 2 plus 3 should be 5, 5 plus, and then 3 plus 5 equals 8, 5 plus 8 equals 13, and so on. I mean, that's the way it works, the Fibonacci sequence or numbers, whatever you call. So basically the recursive solution can be written as, it's little bit different than simple one-liner solution. It can be like you are defining, this is the result, this is your number, you predict the number in this sequence, Fibonacci sequence, and then the first one is if I be n minus 1, fib n minus 1 plus fib n minus 2, because you are always uh, retrospecting past two numbers. You are not going back, I mean, in case of factorial, we were going back to the past number, the past product. Then, but in this case, we are going back to past two numbers and get a summation of those. So your base cases should be n less than equals 0 and or n equals 1. So let's see how it works. I mean, how could we code it? So you start it with this type of definition. This is standard. Now if something happens that your n, this one, n less than equals 0, it can well happen, right? Because you are reducing, keep on reducing the number. So if n less than equals 2, then it returns 0, and if n equals 1, then it returns 1. That's pretty simple. So these are the base cases we can calculate. Like for example, 0 and 1, if you think about that, and if you try to find this x here, so if you apply this formula, then x should be fib n minus 1, that is your so basically you are doing what? You are doing third number. So so basically you are calculating what? You are calculating let's do the calculation by let's not predict something. Let's calculate it by using our code so that we know better about it. So let's do this in the programming mode. Rather than explaining something, writing the program is better. So you can say fib.cpp, and then we can start it by simple logic like let's see. So you can start with simple headers, not the logic, I'm sorry, headers. So your header can be include IO stream. First one is the IO stream, input output stream. Let's do that. Then prototype, if I be n, okay, so integer n, int main return 0. So you can say that sorry, here cout, you can say uh, enter n. So you are calculating n Fibonacci numbers, n numbers in the Fibonacci sequence. So what does it mean? If you have just three numbers, so 0, 1, and then 1. Third one is 1. So here uh, we can say in n. Now we have to put int n here, and then cout. So cout won't be like that. You have to write a for loop. So you can do int I equals 0, I less than n, I plus plus. Now each step, each iteration, you will calculate the function. So cout fib I end line. So, or you can do it better. You can make it like give a space. So it will give little bit of formatting as well. So that's the way we can print it. And now we can define the function itself. Int fib n means integer n. Then what we can do, if base cases n less than equals 0, then you can return 0. Okay. Then you can say else if n equals 1, then return 1, right? So these are the base cases. And then you can say the real Fibonacci sequence calculation. So you can do return fib n minus 1 plus fib n minus 2. That's it. So, if you write 3 here, so then you let's see how it works. So in the um, from 0 to 1, how does it go? Like you say 0 fib 0, that means you get 0 minus 1, which is 0, and of course fib 0 means 0 minus 1, and this should be 2, sorry, and 0 minus 2, fib minus 2 equals 0. So you start with 0, then 1 means you have still fib 0, which is 0, fib minus 1 equals 0, then you have 1, and then 2, I mean third number, it should be like 3. That means 3 minus 1 is what? 3 minus 1 is 2, and this is 1. So 2 plus 1 equals, I mean, sorry, uh, 3 means you have, sorry, 2, 0, 1, 2. 2 means uh, this is 1 and this is 0. So it becomes 1. So that's how it will evolve. So if we simply compile the code, let me switch up the debug console, fib.exe. So we compiled it, and then let's calculate it. So enter n. Let's say I want to print first 10 numbers in Fibonacci sequence. So it will look like this. It's not very good, does not look very good. So let's format it correctly. Cout end line. So now if we re-execute it, it should look like, sorry, not this way. We have to recompile and then execute. So 10. So you can see, so 0, 1, 1. So then pass two numbers, 1, 1, 2, then 1, 2, 3. I mean, it goes as expected. So that's the way we should do. I mean, we can define it. So first of all, in this case, we are formulating the problem. That's the first case. That's part of your problem solving effort. Then you simply establish the base cases, which is this one. So you have to have a return pathway, and then you just keep on calculating this one up to 10. So then you get, for each number you get that I mean that expression. Okay, so that's how you calculate the Fibonacci sequence of first n numbers. So you can have the recursive linked list as well. So recursive functions can be members of a linked list class. Some application maybe compute the size of, I mean, compute the size of number of nodes in a list. So let's see how we can do that. So, or you can do this traverse the list in the reverse order. So basically iterating the list or calculating the size of how many elements are there in a list, you can use the recursive operations. So how do you do that? Counting. So you use a pointer to visit each node. Now algorithm is the pointer starts at the head of the list. So you remember from our past class, the linked list has two attributes. One is the data and another is the node. So you have the data and node. That's your linked list. Sorry, data and a pointer to your next node in the list. So that's how the linked list is formed. So if there is no next node, only one node, then you have, so here there is no next node, for example. So this will be null. The pointer will be pointed to null. This will be a null pointer. That's the basic of the linked list. Now, when you calculate the number of nodes, then what you do, you use a pointer to visit each node. Okay. Pointer starts at the head of the list. If the pointer is a null pointer, we can return 0. That's the base case, you know. So otherwise, you can return 1 plus number of nodes in the list pointed to by the current node. So I mean, it's in the number list. You can see this class in chapter 19 in the previous chapter. So basically, what you can do here. Uh, so let's see if I can find out so that it will be more interesting if we can find the totality of this problem. Just 1 second. Let me try to open it up. So again, we are we are calculating the number of nodes in a linked list. So in the linked list, as I said, it has some data and it has some pointer to the next node. I'm talking about singly linked list. So then you have this count nodes can be the function can be look like this. I mean, you can have the list node, that is the node, I mean, that is the object containing each node for the linked list. So you have the node pointer, that is the pointer to that object. Then if your node pointer is not equals null pointer, so if your node, for example, if there is nothing, then I mean, if there is an, it is not pointed to a not null node, then you should do return 1 plus, then you do the count node next. Otherwise, if it is pointed to nothing, I mean, there is no node at all there, then you should return 0. That's your size, 0. I mean, there is nothing there. That's how you calculate. So return equals 0. This is the base case, whereas this other case, this one, it is the recursive case in this case. So you can also count a list in a reverse order. So pointer starts at the head of the list, and if I mean content of a list in the reverse order. So your pointer starts at the head of the list. If the pointer is a null pointer, then return. That is your base case. Now, if the pointer is not a null pointer, you advance to the next node. Now, upon returning from the recursive call, your display content will be just in the reverse order, you know. So display content of the current node and that the contents of the current node, and that will be your reverse order. So it will be like this. So you have list node, this is a pointer. Then if the node pointer not equals null pointer, then you do the show reverse. So this is something you do, I mean, this is a separate function. Then you show the next node in the reverse order, and you just see out those values. Now the show reverse function is executed by a public display backward function. So it can be like this display backward and show reverse. In this way it can be done. So I mean, basically we don't have I don't find the examples. I will try to find the examples, but I could not locate it. So if I could locate it, I could show it by doing the program here explicitly because linked list itself is a big program. We don't have that much time to write the full linked list program, but that's the idea. I'm just illustrating the idea here. So another good example is recursive binary search function. So binary search algorithm, binary search algorithm involves um, basically you define you compare the left you define, let's say you have an array, so you divide the array into an hierarchy in a way that you always have a left node and the right node. Okay, so your left node can be then you compare left node with the right node and you organize them in a way that your left node is always less than your right node. Right is more than left. So the base case is the desired value is found. I mean, whenever we do the search, that is our desired case that is found. No more array elements to search. Algorithm is now the assumption is whenever you do the binary search, your array should be in an ascending order. If it is a random list, you cannot apply binary search. You have to sort it first. Now, if the middle element of array segment is desired value, then it is done. You know, so in the binary search, you have an array, right? So you have number of nodes there, number of elements there. Let's not talk about nodes. Let's talk about elements. So what it does, let us say it has 1, 2, 3, 4, 5, 6, 7. So the middle node can be like 1, 2, 3, maybe the fourth node is the middle node. You can think about like that. Then if it is the desired function, then you are done. I mean, you found it. Otherwise, if the middle element is too large, then you repeat the binary search in the first hub of array segment. Else, if the middle element is too small, then repeat binary search on the second half of the array segment. So basically, that's how you have to define. So you have a number, right? You are given a number, 5, let us say. So you are not number, you are trying to search a value 5 in an array. You don't know what are there. Let's say you have 1, 2, 3, 4, 5, 6, 7, and 9, 10, this type of array, because this is ordered. Then uh, your middle node is 5. Now you are trying to search 4. That means what? That means it is middle element is high, large, too large or large. I mean it's large. So in that case, your search will be confined within the first hub. So basically, you can think like this one. Let me open up the writing pad. Just a second. So here you are. So let's say you have an array like this. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So your middle node um, should be the seventh one. That's your middle node. So basically 13 by 2 plus 1, that's your middle node. So 13 by 2 is 6. I mean, if you take the whole number plus 1. Now, let's say we are trying to search 4. So then you go to the middle node. Now, middle node you have 7, right? Is 7 too high? Yes, of course. 7 is higher than 4. So then you know that your search domain is here to the left. Now you find its middle node. So you have 6, 5, 4, 3, 2, 1. Its middle node can be, let's say 1, 2, 3, 4, 5, 6. So third row. So this one may be your middle node row. So now the 4. You are searching for 4. It is high or low? It is low. So your domain is towards the right. So your domain becomes this one. Now take the middle point 5. 5 is too high or too low? 5 is too high because 4 is less than 5. So you now you are just searching on this particular part. So you should be towards the left. So you get 4. So this is just one element. So that is your result. So you found it. So that's how you are supposed to do the binary search. It's very fun way of searching things. It is because in the first part you are eliminating a lot of complexity because you if you do it in an iterative way like writing a for loop, then you will do a lot of like your complexity or your cost would be n because you have to run through the n number of elements. But here you are in the first place you are reducing it to half. Now it may be so that your midpoint is the point you found, then you got it immediately. But otherwise you have to go through every step you are reducing the number of iterations to half. That's the advantage of binary search. But in case of if you want to do the recursive binary search, then you can do it in this way. So you write a function called the binary search. So you have an array, right? Array is your number. That is the number of your interest. So the first, this is last, this is the value. So what you can do here, the first is the first number in the row, last is the last number in the row, and value is whatever you want to find. So we have to find out the midpoint. So first of all, if first is greater than last, then that does not make any sense. You are not on ordered list. So then return -1. So it's bad. Now the middle row should be the first plus last divided by 2. So in this case, first is the index of the array. Essentially, this is the index. First and last are the indexes of the array. So if you have, let's say, first index is 0 and last index is, let's say, 11, you have the 10 elements. So total 0 to 10. So you have the 5 as the midpoint. So then, so you identify the midpoint. So now you do if array middle, the middle point, whatever value is equal to, if it is the value, then you return middle. If middle is less than value, means it's towards the left side, then you return binary search. Again you do what you do here, you do middle plus 1 because your value is more than value is too high, so you go towards right. So you start with middle plus 1, the next row, next next number to the last number. So middle plus 1 last, and then you write the value and then let the system process it. Otherwise, so every time it goes here, then it evaluates if the middle value of the new row, new binary array, new array is the value is less than middle value or more than middle value. Now otherwise it will just go towards left. That's how it makes the calculation. So at the end of the day you should find out the, I mean, your value. So you will see that you will get it in much less of iterations compared to your for loops. There are other problems like famous problems, the Towers of Hanoi. So Towers of Hanoi is a mathematical game that is often used to demonstrate the power of recursion. The game uses three pegs and a set of disks stacked on one of the pegs. So this is just an illustration. The object of the game is to move the disks from the first peg to the third peg. So you are moving the disk from the first to third. So rules is only one disk may be moved at a time. So you are basically able to move one disk at a time. A disk cannot be placed on the top of a smaller disk. So, you just place it here. You cannot just place the next disk on the top of this one. So it's a little tricky. All disks must be stored on a peg except while being moved. So they have to be there. I mean, if if you solve the problem, no matter what the algorithm is, you would do what? You would simply um, put this one, take this one, put it here, take the second one, put it here, take the third one, put it here, and then you take this one, put it here, bottom, second one, put the next, third one, put the top, put at the top. But this is very costly because it will take a lot of lot of to and fro for loops basically. So I mean that's what I said. I mean that's what I illustrated, right? I mean this one. So you do it, you put it there. So you have it. So you keep on putting things at a certain place, and then you keep moving the stuff. So you could do like these are these are the possible moves here. Now the following system describes the overall solution of the problem. Move n disks from peg 1 to peg 3 using peg 2 as a temporary peg. That's what we also proposed as a solution. Now algorithm is to move n disks from peg A to peg C using peg B as the container, temporary container. So then if n is greater than 0, then move n minus 1 disks from peg A to peg B using peg C as the temporary peg. Now move the remaining disks from peg A to peg C and move n minus 1 disks from peg B to peg C using peg A as temporary peg. So just go through the solution and try to write it down. I mean, uh, go through each of the picture here and write down your solution and compare. That way it will be pretty transparent. Now, if you write it in a programming language, it will be little different. I mean, you see, this is your move disks prototype. You have four variables there. So you have the number of disks, you have from peg, you have to peg, and temporary peg. So you can call this function, and then this can be like this. I mean, if the number is greater than 0, so you have this, you define it in this way, move disk number minus 1, and then you can say from peg, temporary peg, to peg. So these are all given here. So now you can keep calling it recursively, like you do it in the first place and then you do it again. So you are doing two movements. So these are the two movements that you have done. So that way you will be, that is your base case is covered by number greater than 0. If number is not greater than 0, then you exit. I mean, there is nothing, no way to go. So you are not doing anything, your disks are completely organized. So if you do the program, I mean, if you write it, it will look like this if you execute the program. So basically, let's try to execute it. Let's try to see this. Let's create a new code called disks or hanoi.cpp. Okay, let's uh, let's do the header first. So we get the standard headers. Then we create the prototype as we explained in the slide. That is our prototype. So we can do now main function return 0. Then we can just put together the inputs like number of disks, how many disks are there. So this is the number of disks. Now come the from peg. So 1, 2 peg, that is 3, and then finally temporary peg is 2. So if you do that and then you can play the game, just you do move disks. Okay, so you can say that all pegs are moved at the end. So now we can code the move function. That can be like this. Then you say if number greater than 0, then you simply do this pieces. So you come here. Now it will print each step here. Now let's save this code. Let's compile it G++ and then we can say Hanoi.exe and then Hanoi.cpp. Something is wrong. We did not save it, or what's going on here? Undefined. Oh, okay. The main function. Oh, main. It should be main. I forgot the letter M. That's quite interesting. So if I do that now, we can now execute. So you can see that recursively it goes. I mean, move disk from peg 1 to peg 3. So you do that, and then you move a disk from peg 3 to peg 2. Then you move a disk from peg 1 to peg 3 again, and then so basically what you do, you remember your picture. We did it in a little bit more efficient way than I described there, because what I describe is a very simple, like they can say, you can tell brute force way. But here, what you do, first one goes here, second one goes here. So let me delete this one. Eraser, use some eraser here. Okay, so let me do the pointer. So first one goes here, second one goes here. Third one you don't put it here, third one put here. Then you just take these two from here, I mean, and then put them back here. That's still, no, sorry. Then these two means, I mean, the first one should be this one. So you have 1, 2, and 3, right? So 1 goes bottom, 2 goes top, then 3 comes here directly. Then you put 2 on the top of this, and then you put 1 on the top of this. This is better than the previous approach that put everything there and then reverse it. So that way this is an example of recursive solution, and you can see that we already gained tremendously if we employed some recursive solution. So I think that's it. That's all I wanted to I wanted to present today. Um, any question? Well, if not, you can always ask me for an office hour, because next week is the final. You are more than invited, I mean, more than welcome to to ask me for an office hour. And you can ask me anytime. Just ask me that you need some help. Then I will find some time for you within a day or so, and I will be able to help you. Because since next week is the finals week, we should be a little bit more flexible. So this weekend, I will be available on Sunday. Um, Tomorrow, I will be available. If you need some help, you can ask me for tomorrow. Uh, Saturday, won't be available. Sunday, I will be available. And then Monday to all the way to Wednesday, I will be available during the daytime primarily. So, just in any case, if you need any help, let me know. And you have time to solve your rest of the problems throughout June the 3rd, and your final is next week. I'm going to put together an announcement about the final so that we know exactly when we are doing the final. And before final, I will do all the grading so you will know exactly the math for your final. And yeah, that's about it. And that's it. And so if you don't have any more question, then thank you and good night.